Nitrogen and its compounds. Nitrogen was first discovered in 1772 by a Scottish physician and chemist, Daniel Rutherford, but its elementary nature would be proven later by Priestley. Free atmospheric nitrogen exists as a diatomic molecule. In chemical combinations, nitrogen is found as a mineral deposit in the form of sodium nitrate, ammonium sulfate, potassium nitrate, calcium nitrate, and many others. In living things, nitrogen is found in all proteins, nucleic acids, and some vitamins. It belongs to group 5 and period 2 of the periodic table with an electron configuration of 2 to 5. It is generally unreactive, which makes the atmosphere somewhat inert, slowing down the oxidation of matter. The approximate composition of air is 78.08% nitrogen, 20.95% oxygen, 0.93% argon, 0.04% carbon dioxide, and between 0 to 4% water vapor. Nitrogen, argon, and oxygen can be separated from air by liquefaction, followed by fractional distillation. Firstly, the air is filtered to remove dust. It is then cooled in stages to negative 200 degrees Celsius, at which temperature air is a liquid. As it is cooled, water vapor condenses and it is removed by absorbent filters. Carbon dioxide is then removed at negative 79 degrees Celsius when it freezes. The oxygen liquefies at negative 183 degrees Celsius, argon at negative 186 degrees Celsius, and nitrogen at negative 196 degrees Celsius. The liquid nitrogen, oxygen, and argon are then separated by fractional distillation. First, as we said before, the air is cooled to negative 200 degrees Celsius and passed into the fractionating column. It is then gently warmed. The temperature rises from negative 200 degrees Celsius, and when it gets to minus 196 degrees Celsius, the nitrogen boils out and is collected. When it reaches negative 186 degrees Celsius, the argon boils out, and at negative 183 degrees Celsius, the oxygen boils out. In the laboratory, nitrogen is prepared by heating a solution containing equal amounts of ammonium chloride and sodium nitrite. In this experiment, sodium nitrite reacts with ammonium chloride to form ammonium nitrite. This is an example of a double decomposition reaction. Ammonium nitrite is unstable and decomposes on heating, giving out nitrogen gas. Ammonium nitrite is very unstable and decomposes even at room temperature. For this reason, it cannot be stored. This explains why it has to be prepared fresh by reacting sodium nitrite and ammonium chloride. If dry nitrogen gas is required, it should be passed through a U-tube containing beads wetted with concentrated sulfuric acid and then collected in a syringe. Nitrogen prepared in this method is pure and free of noble gases. It is less dense than the one prepared by the removal of oxygen and carbon dioxide from air. Physically, nitrogen is a colorless, odorless, and tasteless gas. It's slightly less dense than air. It's slightly soluble in water. It has a boiling point of negative 196 degrees Celsius. It doesn't burn nor support combustion. It's a neutral gas with no effect on litmus paper. Some of the important uses of nitrogen are creating an inert atmosphere for chemical processes. The Haber process for the manufacture of ammonia, gas chromatography, packing oxidizable foods such as ground coffee, and also liquid nitrogen can be used for the freeze drying of foods and preservation of tissue samples. Chemically, nitrogen gas is highly inert under ordinary conditions of temperature and pressure. It neither burns nor supports combustion. The inertness is due to the presence of a triple covalent bond between the two nitrogen atoms, forming a nitrogen molecule. The bond is very strong and requires a lot of energy to break. Nitrogen does, however, react with some substances under certain conditions. In air, nitrogen and oxygen will combine when heated to a high temperature in the presence of a platinum catalyst to form nitrogen 2 oxide. This is a reversible reaction. The nitrogen 2 oxide is immediately oxidized further by more oxygen to nitrogen 4 oxide. Nitrogen 2 oxide is formed in the atmosphere during thunderstorms under the influence of heat produced by flashes of lightning. Nitrogen and hydrogen will combine when heated in the presence of an ion catalyst and high pressure to form ammonia. This reaction is used for the industrial manufacture of ammonia. Nitrogen will also react with highly reactive metals when heated to form metal nitrides. Examples of such metals are sodium, magnesium, and calcium. In particular, magnesium burns brilliantly in a jar of nitrogen to give magnesium nitride. The nitrides are easily hydrolyzed even by cold water, giving off ammonia and the metal hydroxide. Sulfur does not react with nitrogen even when heated. Oxides of nitrogen. Nitrogen forms the following common oxides: nitrogen 1 oxide, nitrogen 2 oxide, nitrogen 4 oxide. All these are gases at room temperature and pressure. Nitrogen 1 oxide. Nitrogen 1 oxide is commonly called dinitrogen oxide or nitrous oxide. It is prepared by gently heating ammonium nitrate. The reaction is exothermic and may become explosive if heated strongly. As a precaution, heating is discontinued after about 2/3 of the solid has decomposed. The gas is collected over warm water in which it is only slightly soluble. The gas can also be prepared by heating a mixture of any ammonium salt and a nitrate that will yield ammonium nitrate. For example, ammonium sulfate and potassium nitrate. The ammonium nitrate decomposes, giving off nitrogen 1 oxide. This method is safer with less likelihood of explosion as compared to the use of ammonium nitrate as the starting material. Physically, nitrogen 1 oxide is a colorless gas with a faint sweet smell. It is fairly soluble in cold water but less soluble in hot water, and this explains why it is collected over warm water. An aqueous solution of the gas is neutral to litmus. It is about 1.5 times denser than air. Chemically, nitrogen 1 oxide has no effect on red or blue litmus papers, showing that it is neutral. Burning metals, for example magnesium, and non-metals like sulfur and charcoal continue to burn in the gas, forming the corresponding oxide and nitrogen gas. A feebly glowing wooden splint does not relight when placed in a jar of nitrogen 1 oxide. However, a vigorously glowing one relights. This shows that nitrogen 1 oxide itself does not support combustion. However, at high temperature of about 600 degrees Celsius, it decomposes to oxygen and nitrogen, and it is the oxygen so formed that supports the combustion of various substances. The reaction between burning elements and nitrogen 1 oxide are oxidation-reduction reactions. The elements are oxidized to their oxides while nitrogen 1 oxide is reduced to nitrogen. Nitrogen 1 oxide is in this case the oxidizing agent. When inhaled, nitrogen 1 oxide has a mild anesthetic effect. When mixed with oxygen, it is used as an anesthetic for minor surgical operations, especially in dental surgery. Patients recovering from nitrogen 1 oxide anesthesia may laugh hysterically. As a result, the gas is commonly called laughing gas. Next, nitrogen 2 oxide. Nitrogen 2 oxide is also called nitrogen monoxide or nitric oxide. It is usually prepared by the action of moderately concentrated nitric acid on copper tannins. Effervescence is observed as nitric acid reacts with the copper tannins, forming nitrogen 2 oxide. Initially, brown fumes are observed in the flask, but they soon disappear. This is due to the oxidation of nitrogen 2 oxide to nitrogen 4 oxide by oxygen present in air inside the flask. The nitrogen 4 oxide, however, dissolves in the water, over which nitrogen 2 oxide is collected as a colorless gas. Physically, nitrogen 2 oxide is a colorless gas. It is only slightly soluble in water, forming a neutral solution. Its smell is unknown since on exposure to air, it combines instantly with oxygen, producing brown fumes of nitrogen 4 oxide. Chemically, nitrogen 2 oxide does not burn nor support combustion. However, it decomposes to nitrogen and oxygen at temperatures above 1000 degrees centigrade. The oxygen so formed will support the combustion of burning substances. Therefore, nitrogen 2 oxide will support the combustion of fiercely burning substances like magnesium and phosphorus, which produce heat over 1000 degrees Celsius. These are oxidized to their corresponding oxides, shown by the following equations. It will, however, extinguish a burning wooden splint and sulfur, both of which are not hot enough to cause its decomposition. Also, nitrogen 2 oxide oxidizes hot metals, for example copper and iron, to their oxides and is itself reduced to nitrogen. Again, nitrogen 2 oxide is instantly oxidized by atmospheric oxygen to nitrogen 4 oxide. An interesting reaction occurs between nitrogen 2 oxide and iron 2 sulfate solution. Nitrogen 2 oxide dissolves in cold iron 2 sulfate solution to give a dark brown solution of nitrous iron 2 sulfate. This reaction is used for detecting nitrogen 2 oxide. It is also the basis of the brown ring test for nitrates. If the nitrous iron 2 sulfate is heated, nitrogen 2 oxide is released. Nitrogen 2 oxide is used in the manufacture of nitric acid. The process involved will be described later under synthesis of nitric acid. Next, nitrogen 4 oxide. Nitrogen 4 oxide is commonly called nitrogen dioxide. It is a poisonous substance and should therefore be prepared in a fume chamber or in the open. It is usually prepared by the action of concentrated nitric acid on copper. The gas is collected by downward delivery or upward displacement of air because it is denser than air itself. A more pure form of nitrogen 4 oxide can be prepared by heating a nitrate of a moderately reactive heavy metal. Lead 2 nitrate crystals are the most suitable because, unlike most other nitrates, they do not contain water of crystallization, which would interfere with the preparation. Physically, nitrogen 4 oxide is a dark brown gas. It has an irritating pungent smell. It is 1.5 times denser than air. It is easily liquefied on cooling, and it is highly soluble in water. Chemically, nitrogen 4 oxide reacts with water on dissolving to form a solution which contains nitric acid and nitrous acid. The solution turns a blue litmus paper red. If the solution is shaken vigorously with air, the nitrous acid is oxidized by oxygen to nitric acid. Nitrogen 4 oxide does not burn nor support combustion. However, it decomposes to nitrogen 2 oxide and oxygen at high temperatures. It extinguishes a glowing splint. This is because the temperature of the splint is not sufficient to decompose the gas. Vigorously burning substances like magnesium, phosphorus and sulfur will continue to burn in the gas, and this is because the temperatures produced are sufficiently high enough to decompose the nitrogen 4 oxide into nitrogen 2 oxide and oxygen. The nitrogen 2 oxide is decomposed further into nitrogen and oxygen. The burning substances are oxidized to their corresponding oxides, and nitrogen 4 oxide reduced to nitrogen. In the same way, nitrogen 4 oxide oxidizes white-hot copper or red-hot iron to their corresponding oxides. Nitrogen 4 oxide reacts with alkalis to form a mixture of a nitrate and a nitrite salt in equivalent amounts. For example, with sodium hydroxide, it forms a mixture of sodium nitrate and sodium nitrite. The main use of nitrogen 4 oxide is in the manufacture of nitric acid, a process we'll discuss later. Next, ammonia. Ammonia, which is a gas at room temperature, is a compound of nitrogen and hydrogen. It is referred to as a hydride of nitrogen or a nitride of hydrogen. It is produced naturally by decaying nitrogenous organic materials such as proteins. Ammonia is prepared by heating a mixture of any ammonium salt and an alkali. The commonly used reagents are ammonium chloride and calcium hydroxide. On heating the mixture, ammonia gas is evolved. The gas is less dense than air and is therefore collected by upward delivery or downward displacement of air. It is highly soluble in water and cannot therefore be collected over water. Ammonia gas is dried by calcium oxide or quicklime. It cannot be dried using the usual drying agents, for example concentrated sulfuric acid or calcium chloride, because it reacts with them. With sulfuric acid, ammonium sulfate is formed. With calcium chloride, solid complex compounds such as tetraamine calcium chloride are formed. Physically, ammonia is a colorless gas with a characteristic choking smell. It is less dense than air and is easily liquefied under pressure. Ammonia is very soluble in water. It is demonstrated by the rapid rise of water in a jar of ammonia inverted in a trough of water, otherwise known as the fountain experiment. A fountain experiment is used to show the high solubility of ammonia in water. Phenolphthalein indicator is added to water in a beaker. Concentrated ammonia is added into a flask. This is warmed to release ammonia gas. The flask is corked and placed upside down, connected to the beaker via a narrow tube. Water rises up the tube and soon after reaching the flask, a fountain is seen and the water turns pink, indicating that the solution is basic. Low pressure in the flask sucks water up the tube. Because of its high solubility, a large volume of ammonia gas dissolves in the first few drops of water that arrives, further lowering the pressure and thus creates a large suction effect in the flask. This shows that ammonia is highly soluble in water. In fact, 1 volume of water dissolves 800 volumes of ammonia at 15 degrees Celsius. When ammonia dissolves in water, most of the ammonia molecules remain as ammonia molecules surrounded by water molecules, that is hydrated ammonia molecules. A few ammonia molecules, however, react with the water molecules to form ammonium and hydroxyl ions. The presence of hydroxyl ions makes the solution alkaline. The solution formed is called aqueous ammonia solution. It has a strong smell of ammonia. The ammonia is completely expelled from the solution on boiling. This way, ammonia solution serves as a convenient source of the gas. Chemically, ammonia turns a red litmus paper blue, showing that it is an alkaline gas. Ammonia does not burn in air, nor does it support combustion of burning substances. It extinguishes both glowing and burning wooden splints. Ammonia does not burn in air. However, it will burn in pure oxygen or in an atmosphere rich in oxygen with a greenish-yellow flame, forming nitrogen and water vapor. In the presence of a catalyst, ammonia burns in oxygen, forming oxides of nitrogen. Catalytic oxidation of ammonia. In the presence of a catalyst, ammonia burns in oxygen, forming oxides of nitrogen. This can be demonstrated here. We use concentrated ammonia as the source of ammonia gas. A platinum wire is then heated and suspended in the flask containing ammonia. Ammonia and oxygen react on the platinum surface. Platinum catalyzes the oxidation of ammonia to nitrogen 2 oxide, which further reacts with oxygen to give nitrogen 4 oxide. The oxidation is exothermic and keeps the platinum red hot so that the reaction does not slow down. It continues glowing red hot until either ammonia or oxygen is depleted. Besides platinum, other catalysts can promote the oxidation of ammonia. A classic example is chromium 3 oxide. When heated chromium 3 oxide is added into the flask, a shower of bright sparks is seen and water vapor condenses on the sides. The oxidation in this case is, however, less efficient. Reactions of aqueous ammonia with metal ions. Aqueous ammonia reacts with some metal ions to form hydroxides. The hydroxides are insoluble in ammonia solution and form precipitates, some of which are white and others are colored. Some of the hydroxides, however, dissolve in excess ammonia, forming solutions, some of which are colored and others are colorless. These reactions are used in the identification of the cations. When ammonia dissolves in water, some molecules of ammonia react with water molecules to form ammonium and hydroxyl ions. The hydroxyl ions react with metal ions to form hydroxides. For example, with zinc, lead, magnesium, aluminium, calcium, iron 2, iron 3, and copper 2 ions, the corresponding metal hydroxide is formed.
Now what you've seen there is magnesium ions added some small amount of ammonia solution, and you can see a white gelatinous precipitate has formed. So you first add small amount of ammonia solution, we see what happens, and then try and see if we'll have a two-step reaction. How? By adding excess amount of ammonia solution. What we are going to look for is whether that precipitate will dissolve. Adding more ammonia solution, let's see what happens. And we are going to add even more and more ammonia solution and see whether the precipitate dissolves. Well, from my point of view, it doesn't look like there is any hope it's going to dissolve, but we are still going to add more and more and shake. But yes, I'm right, it is not going to dissolve. Next I have aluminium ions, and I've added small amount of ammonia solution. The white precipitate there has already formed. When we shake, we'll see whether this precipitate will redissolve. So what we are going to do is that we are going to add excess amount of ammonia solution and see whether that precipitate will redissolve. So we add more. And more, and clearly there is no sign that this precipitate is going to dissolve. The precipitate has persisted. Next in line is zinc ions, and I've added small amount of ammonia solution. A gelatinous white precipitate has already formed. Now our idea is to see whether this could be a two-step process, and we are going to add excess amount of ammonia solution and see whether the precipitate will redissolve. I can already see signs, it's like it's going to dissolve. So let us add more ammonia solution, and the precipitate has started disappearing. we expect a clear solution. We expect a colorless solution there, and that's what we look like we are going to get. Yes, the precipitate has disappeared. It has dissolved in excess ammonia. Next on the line, ion to ions. Already added small amount of ammonia solution. The green precipitate has formed. Now again, just as in previous cases, the idea is to see whether this could be a two-step reaction. What we are going to do is find out if this precipitate will dissolve in excess ammonia solution. So we'll keep adding more and more and try and see if it redissolves. So for the second one, nothing changes, the precipitate still persists. I'm going to add even more and see whether it will disappear. Will it? No. Looks like there's no hope that this is going to go away. So it's a one-step reaction. Next on the line, ion 3 ions. Beautiful brown precipitate formed there with small amount of ammonia solution. We add more. As we shake and we see the brown precipitate persist, we are still going to add more ammonia solution and see whether that precipitate will redissolve. So more drops, nothing seems to change, the brown color only is. Let's try and see. The brown precipitate still persists and doesn't look like it's going to dissolve. So it's a one-step reaction. The brown precipitate persists. Finally, we have copper. No mistake. Blue color of copper 2 ions. Copper 2 ions in ammonia solution. Small amount of ammonia solution. Blue color there appears. We are going to add more ammonia solution and see if that blue color will disappear, or at least if there will be another step. Keep shaking and see. We add more and more ammonia solution and see what happens. Now you might notice the blue color is deepening with time as we add more and more ammonia solution. So let's keep going. The precipitate appears to be dissolving. From far I can see a deep blue solution that is being formed. We can get a better shot of that. Yes. Add more. Looks like there is going to be another step. Yes. A deep blue solution is being seen from very far. And yes, the precipitate appears to be dissolving. Adding more ammonia solution and the precipitate has redissolved. The precipitate has redissolved to form a deep blue solution.
Zinc hydroxide and copper 2 hydroxide react with excess ammonia, forming soluble complex ions. With zinc hydroxide, tetraamine zinc ion is formed. With copper 2 hydroxide, a tetraamine copper 2 ion is formed. When exposed to air, concentrated hydrochloric acid releases hydrogen chloride gas. The gas reacts with ammonia, forming white fumes which consist of tiny solid particles of ammonium chloride. Industrial manufacture of ammonia, the Haber-Bosch process. Ammonia is produced on a large scale using the industrial implementation by Carl Bosch in 1913 and the laboratory scale ammonia synthesis developed by Fritz Haber. We've seen ammonia is a compound of nitrogen covalently bonded to 3 hydrogen atoms. To combine the 2 starting materials, nitrogen and hydrogen, to produce ammonia, the bonds in the diatomic molecules have to be broken. Under high pressure as well as temperature, nitrogen adsorbs onto an ion-based catalyst and is split up into atoms. Hydrogen can now be adsorbed and ammonia is produced. The catalyst itself remains unchanged. This reaction generates heat, and therefore, the reacting hot gases and ammonia reactor are cooled with the supply of a cold gas. This is achieved with a sophisticated flow system of synthesis gas based on the heat exchange principle. This way, the so-called equilibrium reaction can be prevented, in which the ammonia tends to decompose again into nitrogen and hydrogen. The ammonia is collected as a liquid and stored in tanks. The remaining synthesis gas is returned to the reactor and forms more ammonia. An important precondition for ammonia synthesis is the efficient production of pure hydrogen. In several process steps, this precedes the actual ammonia synthesis. In the primary reformer, first, a natural gas methane is heated together with steam to about 800 degrees Celsius and is thereby converted into a mixture of carbon monoxide, carbon dioxide and hydrogen. In the downstream secondary reformer, air is then added and the remaining methane gas is converted at above 1000 degrees Celsius by means of a catalyst, and nitrogen is added. Since carbon monoxide and carbon dioxide will damage the ion catalysts used in ammonia synthesis, they have to be removed. Carbon monoxide is converted to carbon dioxide in a 2-stage process using special catalysts. The carbon dioxide can then be removed by a chemical scrubbing process. What remains is the pure synthesis gas consisting of 3 parts of hydrogen and 1 part of nitrogen, which can now be transferred to the actual ammonia reactor. So the Haber process is the industrial process for the manufacture of ammonia from hydrogen and nitrogen. Hydrogen is obtained from the reaction of methane and steam, producing carbon monoxide as a byproduct. These gases are compressed and delivered to the reactor where ammonia is produced. They are then cooled down and ammonia is liquefied and tapped off. Unused hydrogen and nitrogen are recycled back to the reactor. Note that this is a reversible reaction and that the forward reaction is exothermic. The Haber process uses the Le Chatelier's principle to maximize ammonia production while keeping operation and production costs in mind. Le Chatelier's principle tells us that increasing pressure will favor the side with fewer moles, for our case, the production of ammonia. It would therefore make sense to conduct the reaction at a very high pressure, but we must keep in mind that it is expensive to build an operator plant that can withstand such high pressures. A compromised pressure of 200 atmospheres is used. Keeping this principle in mind, what's the best temperature to maximize ammonia production? Since the forward reaction is exothermic, it would make sense to conduct the reaction at a low temperature. A compromised pressure of 400 to 450 degrees Celsius is used, which is not exactly low, but not too high. If a low temperature was used, the rate of reaction would be slow, though the exothermic reaction would be favored. It would actually take a long time for equilibrium to be reached. So a compromised temperature of 400 to 450 degrees Celsius ensures that the reaction proceeds with sufficient yield. The yield of this process is 10 to 20%. Remember that the unused gases are recycled, so no reactants are wasted. An ion catalyst is used in this process. The catalyst does not affect the position of equilibrium, but only increases the rate at which equilibrium is attained. So in conclusion, the Haber process is the industrial synthesis of ammonia from nitrogen and hydrogen. It is conducted at 400 to 450 degrees Celsius at 200 atmospheres in the presence of an ion catalyst. These are compromised conditions in order to maximize ammonia production and economic profits. Next, nitric acid. Nitric acid is one of the common mineral acids. It is extremely corrosive and will attack almost all metals, rubber and coke. All apparatus used in its preparation and storage must be made of glass. In the laboratory, nitric acid is prepared by heating a mixture of equal parts of sodium or potassium nitrate and concentrated sulfuric acid. The nitric acid formed, being volatile, distills over. The concentrated nitric acid vapors are collected in a water-cooled receiver. The vapors are condensed into a liquid gradually. Pure nitric acid is colorless. However, the fumes appear brown due to the presence of nitrogen 4 oxide, which is produced by slight decomposition of nitric acid by heat. The nitrogen 4 oxide dissolves in the nitric acid, imparting a yellow color. Nitrogen 4 oxide can be removed by bubbling air through the acid. Nitric acid formed in this method is 98% pure and is called fuming nitric acid. On a large scale, nitric acid is manufactured by the catalytic oxidation of ammonia in the Ostwald process. Here we have 4 chambers, namely catalyst chamber, cooling tower, oxidizing chamber, and the absorption tower. A mixture of pure dry ammonia gas and dry dust-free air in the ratio of 1 to 10 is fed into the catalyst chamber. In the presence of the platinum gauge at temperatures of 700 to 800 degrees Celsius, the ammonia is oxidized to nitrogen monoxide or nitric oxide. This is an exothermic reaction. This nitric oxide gas is then allowed to pass through the cooling tower and the gas is cooled to 50 degrees Celsius. The cooled nitric oxide is then allowed to pass into the oxidizing chamber. This chamber has an inlet for fresh oxygen. Here, nitric oxide combines with oxygen to form nitrogen dioxide. This nitrogen dioxide and non-reacted oxygen then flow into the absorption tower, which is a stainless steel tower packed with acid-resistant quartz. Water is sprinkled from the top, so it slowly trickles to the layer of quartz. The water dissolves nitrogen dioxide in non-reacted oxygen to give dilute nitric acid. Nitric acid obtained by this process contains 65% acid and 35% water. Its concentration can be raised further by fractional distillation. It is stored in dark bottles because it slowly decomposes on exposure to light at room temperature and pressure. Chemically, concentrated nitric acid decomposes slowly at room temperature, particularly in sunlight, and rapidly when heated, giving off nitrogen 4 oxide and oxygen. Nitric acid reacts chemically in two ways: one, as a strong acid, and as a strong oxidizing agent. Acid properties of dilute nitric acid. Nitric acid is a strong acid which is almost completely dissociated into ions in dilute solutions. Dilute nitric acid turns a blue litmus paper red, showing it is acidic. It neutralizes alkalis, forming a salt and water only. For example, with sodium hydroxide, sodium nitrate and water are formed. Dilute nitric acid reacts with insoluble bases to form the corresponding nitrate and water only. For example, with copper 2 oxide, it forms copper 2 nitrate and water. Dilute nitric acid reacts with carbonates and hydrogen carbonates, producing carbon 4 oxide, which forms a white precipitate with lime water. With sodium carbonate and sodium hydrogen carbonate, sodium nitrate, carbon dioxide and water are formed. Nitric acid reacts with all metals except gold and platinum. Unlike other dilute mineral acids, that is hydrochloric acid and sulfuric acids, which react with the active metals to give a salt and hydrogen gas only, nitric acid gives a variety of products. Nitric acid only gives hydrogen and a salt when the very dilute acid reacts with magnesium or calcium. The products formed with other metals depend on the concentration of the acid and the temperature. The corresponding nitrate is usually formed, but other products range from hydrogen, nitrogen, nitrogen 1 oxide, nitrogen 2 oxide or nitrogen 4 oxide. For example, with cold, moderately concentrated nitric acid and copper, nitrogen 2 oxide is formed. Concentrated nitric acid acts as a powerful oxidizing agent. It does this by acting as an acceptor of electrons. In so doing, it is reduced to either nitrogen 4 oxide or nitrogen 2 oxide. The electrons are donated by the reducing agent, which may be a metal ion, or a non-metal. For example, concentrated nitric acid reacts with copper, forming brown fumes of nitrogen 4 oxide, copper 2 nitrate, and water. In this case, metallic copper loses 2 electrons, being oxidized to copper 2 ions, which go into solution. The electrons are accepted by nitric acid, which is reduced to nitrogen 4 oxide. Iron and aluminium react with concentrated nitric acid, forming a protective layer of oxide which prevents further reactions. Concentrated nitric acid reacts with acidified iron 2 sulfate, forming nitrogen 2 oxide gas. The green iron 2 sulfate solution changes color to brown. This is due to oxidation of iron 2 ion to iron 3 ion. Colorless nitrogen 2 oxide is immediately oxidized by atmospheric oxygen to nitrogen 4 oxide, which is a brown gas. Again, concentrated nitric acid reacts with sulfur, forming nitrogen 4 oxide gas and sulfuric acid. The presence of sulfuric acid is confirmed by the formation of characteristic white precipitate of barium sulfate when it reacts with barium chloride or barium nitrate. Finally, concentrated nitric acid reacts with charcoal, forming brown nitrogen 4 oxide gas and carbon dioxide gas, which forms a white precipitate with lime water.
You can always spot the brightest minds, the ones who think bigger, who push concepts a little further. When you combine theory with practical study, you get university students that are more switched on. That's why Curtin graduates are ready to make a difference from day one, to help make tomorrow a better place.